Look out, Nerf battle coming your way. Let's jump into this problem. I think it's a really interesting one. I'm excited to jump in. We'll see when we turn this problem on its head, we find a solution. We have a solution really just drop out of the problem that feels really hard to identify from the top. And maybe this will surprise you, maybe it won't, but there'll be a surprising, fascinating constant that drops out when we get to the end here. So let's take a look at the problem statement. In this case, we are commanding a Nerf army where we're going to take turns firing and successfully hitting our opponents, and we're trying to get a sense of, okay, how big does my army need to be in order to win, to lose, or to tie this battle? And the first thing that jumps out at me here is that if we're taking turns, it seems like there's not really any way we would actually end up in a tie. Either I'll have one soldier left and so will you, and he'll fire a Nerf dart and win for my side, or vice versa. And so I think we can actually scratch the tie right out of that list of options. So the question is how big does my army need to be in order to defeat yours? So let's jump in and start trying to analyze that in a little bit more detail. So it's never a bad idea to start out by looking for some sort of patterns, or trying to understand what might bound or be a range of possible values that would satisfy the question that we're asking, okay? We're going to look for patterns to kind of arise and try to allow them to dictate the approach that we take to actually finding the solution. So you can certainly experiment, but it's almost always better to, once you have a handle on what exactly is happening, to try to identify some sort of pattern or structure, and then after that, look for ways to break your pattern, look for ways to break your structure. And so that's exactly what we're going to do. We're going to start with just a simple experimentation, make sure that it's clear what it is that we're doing, and then after that, we'll start to fiddle with the different aspects of a solution here. So let's start with a simple example, then maybe build up a little bit more complicated, just a larger size. Okay, so if I start with 2 combatants, you start with 3, I fire first, I eliminate 2 soldiers, you fire back, eliminate one of mine, and then I use the last soldier to eliminate 2, and it looks like the circles win, okay? Now let's take a slightly larger sample here. What if I start with 5, and you start with 8, okay? And I'm going to take my first shot, and that is going to eliminate 5 of the 8 on your side. You will then have 3 archers and fire. I will be able to take 2 more shots, and then we'll find ourselves in the same situation where you take 1 more shot, and then I take the last shot, and it looks like O's win. Okay, so we're starting to get a little bit of a sense here. That took a bunch of back and forths. The fight there was pretty close. Okay, the next thing that I want to talk about is I want to talk about scale. Okay, so imagine the way that this unfolds if each of those archers, instead of just representing an individual archer, represented 10 or 100 archers, right? So let's imagine I have 2 archers, you have 3, but let's imagine that instead of those representing 1 archer each, those are now 10 archers each. Well, the 20 archers on my side eliminate 20 archers on your side, still crossing out 2 X's, and then your 1 remaining archer will cancel the one of the 2 sets of archers that I have left. And so what we're noticing here is this big idea that scale doesn't matter, okay? So it turns out that it doesn't really matter whether there are 2 and 3, 20 and 30, 200 and 300, or any other multiple. It really matters the relative sizes of our armies, right? And we could actually see this a little bit closer if we, for example, put 4 archers up against 6. You would really start to feel, okay, even though that feels different than 2 against 3, the kind of the fraction and the way that it unfolds along the way would all be the same. The interesting part about 4 versus 6 is there's actually no way that you would end up with an odd number of members of your army on either side of the battle, and that would actually apply for any even number of combatants. And that starts to make me think, right? And so does the fact that when it's close, we end up with, maybe 1 combatant on each side, right? That starts to make me think, okay, well, I want to try to set up this problem so that I can think specifically about the cases where I'm going to end up with a 1-on-1 fight or a 2-on-2 fight, something pretty small at the very end, okay? And so what we're going to do here is we're going to do the kind of the spinning around that I alluded to at the beginning, where sure, we could try a bunch of examples and squeeze the kind of the upper and lower bound of that ratio down until we got closer and closer to that number. But ultimately, there's still going to be some gap in between the kind of the lowest and the largest possible values that would contain our number. And so we need to come up with some sort of solution to find the threshold. And remember, we're looking for a threshold ratio. We need to find a method to find that threshold ratio so that we can then apply that to all situations, right? We'll be able to have a single heuristic that we can use to determine, hey, because you have more than X times as many soldiers as your opponent, you will win, or because you have less than this threshold, you will lose, okay? So let's start out by working up from a small fight, okay? So if I have a single archer and you have a single archer, I would win, right? If you have a second archer, though, you would win because I would only be able to eliminate one of your archers, and then this one-on-one thing would be kind of reversed, right? Well, in order to have enough to take care of that situation, I would need a second archer, right? But, well, that second archer case isn't terribly interesting because I would eliminate both of your archers. So let's head towards something that's a little bit more interesting, which is the 2-on-3 that we looked at earlier, right? Where we know that the X's have just enough firepower here to win. And if you notice kind of the handing off back and forth, it might motivate assigning a number of soldiers such that you'll have just enough to get to another state that's also close. So we started with 1 versus 1. That motivated us to go to the state of 1 versus 2. And I'm going to start listing some of these numbers off. Okay? That motivated us to go to the state 2 versus 3. But in order for this state to happen, well, the only place that this comes from, if it was O's turn immediately before this, was for X to have 5. And if you have messed around with numbers or number theory much, you might start to recognize this list of numbers. You might even be able to jump all the way to the solution, but we're gonna kind of work our way there. What actually ends up happening here, though, is that the sum of these numbers, this 2 and 3, was what was combined to give the next number on the list. And then we kind of just brought this number over to the left, right? You can think of it as the 2 and the 3 from the prior fight, or you can actually, because we're bringing this number down, you can also think of it as the 2 and the 3 from the same side of this column. So you'll notice that this 2 and this 3 makes 5, and if we were to continue this process, we add up the two numbers above and create the next number in the sequence. And I use the word sequence. You might be familiar. At this point, this is called the Fibonacci sequence. Okay, the Fibonacci sequence is specifically constructed by starting with two values, typically 1 and 1, sometimes started with 0 and 1. It ends up with the same result. And then each next term in the sequence is produced by summing the two terms before it. So let's define that really formally. We'll say that a sub 1, the first term in the series, is 1. A sub 2 is also 1. And then a sub n is equal to a sub n minus 1 plus a sub n minus 2. And that might feel a little bit complicated, but let's break that down a little bit more in detail. So for example, if n is equal to 3, we're saying that a sub 3, because again, n is equal to 3, is equal to a sub 3 minus 1, which is a sub 2, plus a sub n minus 2, which is a sub 1. Okay? So you're seeing that the third term is the sum of the first and the second. Similarly, if we'll just do one more here, if n is equal to 4, a sub 4 is equal to a sub 3 plus a sub 2, the two terms that come immediately before it in the sequence. And then if you remember constructing the Fibonacci sequence in the first place, successive terms from the sequence were showing up on each side, right? It was 2 versus 3, it was 3 versus 5, it was 5 versus 8, and so on, okay? And so we're realizing from our approach here that what we actually need is we need the ratio of terms in the Fibonacci sequence, right? Because if that is the situation that consistently is getting us close to a tie, that's most likely going to be the threshold after which, or above which, we would be able to be confident that we were going to win the fight. So what we're looking for is some sort of limit of this sequence. We're not specifically looking for just what the Fibonacci sequence goes to particularly, but we're looking for the ratio between successive terms, right? And probably the best way to write that is the limit as n goes to infinity of a sub n plus 1 over a sub n, right? Whereas, so this is some term, right? And this is the term after. Okay, because once we have that ratio, we can presumably kind of bring that into the context of the particular problem and go from there, okay? So what we're going to do in order to evaluate this, well, we're going to replace a sub n plus 1 with the Fibonacci definition of a sub n plus 1. Remember, it's the sum of the two terms before it. So if n is, say, 5, this would be a sub 6. So we need a sub 5 plus a sub 4, right? And then we're going to divide that by a sub n. And then we have the benefit here of being able to split this fraction into two terms. So a sub n over a sub n, which is just 1, plus a sub n minus 1 over a sub n. And this is really cool. I love when this falls out of a limit, because what we have going on here, right? Let's call this entire left side of the equation L for limit, right? And this is a common technique. Even the use of a capital L is a common approach for this kind of a limit problem. It actually turns out that this thing right here is 1 over L, right? You'll notice that this is n minus 1 over n, so it's the term before over the term that follows it. So that's the reverse of what's going on here. And since we're going for a really, really big value of n, we're going for the millionth term, this ratio, if it does come out to a specific constant value, well, that ratio is going to be the same for one term as it is for the term immediately before it as we get farther and farther out towards infinity. And so what I'm going to do is I'm going to rewrite this entire expression in terms of this L variable. And we're actually going to be able to solve for it, okay? And that might feel a little bit daunting at first, but once we multiply through by L and bring all the terms onto the same side of the equation, we get L squared minus L minus 1 is equal to 0, which we're able to use the quadratic formula on, right? So L is going to equal negative b, which is going to be positive 1 here, plus or minus the square root of b squared, so that's negative 1 squared, minus 4 times a, which is 1, times c, which is negative 1. So that's going to end up being 1 plus 4 all over 2. And you might be familiar with this. This is the famous golden ratio as well as its complement. And those values are roughly 1.62 and negative 0.62. All right. So this one obviously being the positive one from the plus or minus, and this one being the negative from the plus or minus from the quadratic formula there. And there are all sorts of interesting properties about the golden ratio. Not only does it have these famous aesthetic properties, like architecture and all sorts of different things holding these kinds of ratio and it being aesthetically pleasing to the human eye, there's also interesting relationships here. So for example, we know that if we multiply these together, we get negative 1. We know that if we take the sum of them here as they're written, we get 1. They cancel each other out. So there's a lot of offsetting power here, and it's one of the reasons why it can show up in a solution to a problem like this, because we need not only to be able to handle the ratio for the side that is winning, but also for the side that's losing. And so it turns out that it's its own reciprocal. Remember I said when we multiply them together we get negative 1, so if you drop that negative sign and you multiply them together, that would be positive 1, okay? And so if the one player exceeds the one of those two answers ratio of the other person, then they will have enough power to win, and then the other answer can be given as the result for the other person. So let me show you what I mean here real quick. So let's think about a couple of particular cases here. So remember we had this 5-on-8 fight that we won as the X's, right? Well, if you think about the ratio between those, let's do the ratio of O's over X's, right? So the O's over the X's here is 8 divided by 5, which is 1.6, okay? That actually turned out to be just a shade less than the golden ratio, and it resulted in a win, okay? One case that we didn't look at was the case of 3 versus 5. So if the O's had 5 and the X's had 3, that comes out to a number approximately 1.67, which is just a little bit greater than phi, and the result of this is a loss. And it makes sense, right, that as our ratio gets less favorable, right, as the opponent has a larger multiple of ours, we would be more likely to lose, right? And so the end result of this, and I'm not going to go through all of the nitty-gritty details of proving why this is exactly true, but specifically if the O's over X's ratio, if this ratio is less than phi, the result is that you win. And if it is greater than phi, the result is that you lose. And if you want to think about this from the perspective of the second shooter, that threshold ends up being that phi complement that I mentioned. So in order to win, in that case, you have to have an army that's larger than phi complement times the size of your opponent, and the result is exactly the same as what we just demonstrated here. Okay, there are so many different ways that we could think about this, so many opportunities for extensions. It's an interesting problem. One that came to mind for me was something like a snake draft, where you shoot first, and then the opponent, because of the disadvantage of shooting second, gets to shoot twice, and then it comes back to you, and you get to shoot twice. You could do all sorts of different patterns and think about what kind of relationships would fall out between the different sizes of your military might that you would need in order to be victorious in the fight. Like I mentioned at the beginning, I love how this problem, when we turned it on its head and started thinking about it building up rather than seeing our armies get smaller as we fought, that the solution fell out. I love seeing the golden ratio fall out of just about any problem. Thanks for being here. Hope this was interesting. Let us know if you have any questions. Looking forward to hearing from you.